All right, everyone. Welcome to another video on deep learning. This one's going to be about GRUs, gated recurrent units. This is a follow-up video on the video that I made on LSTMs, where we talked about an enhancement from recurrent neural networks that allows it to have both long-term memory and avoid the vanishing and exploding gradient problems that come with recurrent neural network, plain vanilla recurrent neural networks. So diving in to the GRU, it has two gates, update and reset. Contrast that with the four gates that we talked about, the three gates that we talked about in the LSTM. The hidden state in this case, there's no cell state. The hidden state instead acts as both the highway for information and a transformer of information. The GRU is more computationally memory efficient than the LSTM because it has fewer tensors and operations, both. That's mainly because of the less gates. And the GRUs are a more modern interpretation of, or more modern enhancement of the RNN. They were introduced in 2014. You can contrast that with the LSTM, which has been around since 1997. So they're much more recent. So diving into the architecture, we're going to see, okay, let's check out the architecture for a GRU. And let's just dive into the first gate, the update gate. I've highlighted above the update gate here in yellow. And you can see that what it's doing is we're going to call the update gate Z of t. And it's determining how much past information from the hidden state we want to take and combine, how much past information we want to pass to this future state. So what this is doing is combining x of t, h1 of t, you add them together, and you pass them through a sigmoid function. As we remember, the sigmoid function is going to generate a matrix of some values very close to 1 and 0. And then we're going to apply that again, element-wise, to the hidden state. And this is just going to tell us, okay, how much of the information from the past do we want to forget? And if we look at the math here, we have a sigmoid function of the input and the hidden state multiplied by their respective weights. Now you might ask why we need to incorporate the input when talking about how much past information we need to forget. Well, the current input gives us the context for, so given this new information, how much of this old information do we forget? That's really what we're answering in this first gate, called the update gate. And the next gate is going to be called the reset gate. So we just talked about the update gate here, talking about how much past information we need to forget, given a certain new context of new input. Now we're going to talk about the reset gate. The reset gate, highlighted here, looks exactly like, and it is exactly like the update gate from part 1, except its usage is going to be completely different. The update gate is actually, the reset gate is actually going to be used to tell us how much current information, how much previous information to forget, and how much current information to store. So they sound like one and the other, but basically, instead of figuring out how much previous information to pass forward, we want to say how much previous information do we want to store as part of the new information that we're getting in this cell. So the reset gate is really resetting that historical reference and building a new current state of memory or a new current state of knowledge from this cell. So here we are with the math. It's a sigmoid function applied to the input with the weights plus the hidden state with its recurrent weight, with its respective weight. And it's exactly the same as the update gate. However, we're going to see in a second how its usage is going to be different because we're then passing it through we're then adding it to this input here. So once we figure out how much previous information to forget, we're going to add that to the input to create our new current context, right? We have our current input and we're adding it to some remembered historical information to create our current context. And then we're giving that current context, those certain features of the current context, either enhancing them or decreasing them in importance with this tanh function. That's going to output a vector of negative, like values between -1 and 1. So after these two gates, then we've created this current memory context. And the current memory context, I would say, is h of t prime. So this is basically what should be in our new memory, right? We're calling this our new memory. And now it brings us to a final step of, okay, we have our current memory, u of xt right here, the input adds memory, and then the reset gate times the old hidden state with its times its weight determines what to keep from the old memory to create our current memory. But now we have to finalize everything and say, given our current memory state or our current knowledge state, how important is that in relationship to previous contexts and previous memories? And it turns out this is what we're going to be doing with z of t, that reset gate. All we do is take z of t, which is the reset gate, multiply it by that previous hidden state. This is determining what to remember from before. And it's also giving it a weighting of how important is this historical context. And then we're going to add it on to the opposite of that, 1 minus zt, times the current memory context. So what to remember from the current state. What this is all this is doing is saying how important is the current state of knowledge in relationship to the previous state. So for example, let's walk through if we were trying to, determine the sentiment analysis, perform sentiment analysis and determine the sentiment of an Amazon review of a product. Let's say they were testing out a food blender, very random, but the review could start with something like, it could be a long paragraph, and it could start with something like, the product came in a box, it was shipped on XYZ date, I used it XYZ times, and a lot of irrelevant information. And maybe the final thing that really gives you the knowledge on whether they liked it was at the very end, where they said, I would buy this again, or this was actually an excellent product, or maybe it said, I would never buy this again. That information is at the very end of the paragraph, and therefore, we really don't want our model remembering all the information that comes up front because it's highly irrelevant to our sentiment. Therefore, in this case, z of t would be very close to 0, and 1 minus ct would be very close to 1, making us remember our current state much more. Especially in later states, it would start remembering that current state a lot more. Vice versa, if the important information came first and irrelevant information came last, then we would our model would learn to have set the values of z of t to be the opposite. But really, just make sure you know this logic. This is basically the underlying kind of logic of the GRU, and I hope this was helpful. One last thing to note, and I mentioned it in my video on LSTMs, is that the GRU, while more efficient and computationally less intensive, is not necessarily better than the LSTM, and maybe the LSTM actually produces better results in some cases. So what's important and what a lot of people do is end up starting with an LSTM, since it has a little bit more flexibility because of its increased complexity. And then if they can get away with a more efficient structure like the GRU, then they use the GRU. But in general, researchers are testing both of these architectures to see which one performs better. Thanks for the video, everyone. Thanks for the time, everyone, and look forward to seeing you.